Hey guys, welcome back to another video. In this one we're going to be doing this problem. So in this one, let's see, you're the manager of a basketball team. For the upcoming tournament, you want to choose a team with the highest overall score. Score of the team is the sum of scores of all the players on the team. However, the team is not allowed to have conflicts. A conflict, younger players strictly higher score than older. Conflict does not occur between players of the same age. Given two lists, return the highest overall score. Okay. Okay. Okay, so it says you can pick all of them here. Here you want to pick the last three. These three. So 1, 1, okay. Can't pick this because you picked these two. Okay, yeah. It's best to choose the first three players. Okay. Eight, 9, 10. I have this and okay. Oh, because if you pick one with 5, then you can't pick. Okay. Okay. So this is how I'd approach this kind of problem. So first thing, look at the constraints. So we have, this is 1,000. So we can have like an unsquared complexity basically. Then the next thing is like, what are we trying to do? So we can basically pick or not pick players, which is already leaning DP. Then another thing is like, there's probably some kind of sort that's going to be useful because like we want to sort on score or age or something. So some kind of sort. And then with DP, there's basically like a few things we can do. We can have two states, which is like index and previous index we picked or something. Or we can have index and then we have like a loop in there. So something along those lines. So what would be like the maximum amount of information? Like if we had all this information, then we could do this with DP. So that would be like index we're at, last age picked, last score picked or something. And then that way we can like, if we have all of this, then we can probably like get this stuff. But there's also a tricky case where a bunch of scores and ages are like, or a bunch of people of the same age have scores. So that's also tricky. So really what you want is like last age picked below this one, or actually probably like biggest score picked, like biggest score below age. And then something like, yeah, basically current biggest score at this current age or something like that. This would be like way too many things, right? So we need like this and this and this, and this would be like way too much. So basically we want to think about like, how do we want to sort this so we can use DP? And then ideally we either have an O of 1 inside the DP with two states, or we have a for loop in the DP that goes through all of this with one state. So let's think about like, what are all the different ways we could do this? So first of all, the sort, like what do we want to sort on? And then if the first thing is a tie, does the second thing matter or not? Right? Like if players have the same age, does the score sort matter or not at all? Because that's another category you can have that's like an edge case that's like, you know, imagine you have like 3 1s and 3 5s. Does it matter in which way the scores are in that way? So let's say we have the ages like let's say we have that for loop solution where like we say like we pick or not pick, and then we can go to like the next available person, and there's a for loop in there. So basically we're going to always only go to people we are allowed to pick. Let's say that's a solution. So how can we do that? Like what if we sort on, let's think about it, I guess. If we sort on age and we're at some person with some score that we're allowed to pick, how do we know who's the next person we're allowed to pick? We might not necessarily, right? Like let's say the biggest score so far is like 10, or yeah, and this person scores like 15. Well, how do we know that like if a person has score like 9 after this guy, how do we know like if we're allowed to pick them? Like if we skip this guy and if we, and so on. So like score, sorting on score, or sorting on age doesn't seem great. Sorting on score might be better. But if we go on score, then how would that work? So basically, and how would score work? Would it be increasing, decreasing? Like, what if we sort increasing in terms of score? Then how do we know things like that? So I think this is like the tricky part of the problem. It's like a sort order, and so think a little bit about this. Like, what's the best one? Like, do we do in decreasing maybe, and so on. And I think this is kind of like the answer to this problem. Is basically figure out some kind of sort scheme that works. Okay, so, and there's only a few possibilities. So let's just say we try like score increasing, I guess, to start off. So if we do score increasing, and then in terms of age, if there's a tie, if like two scores are the same, then what should we do? Yeah, I think score doesn't make much sense. I think it's more, yeah, because like, okay, well let's just say it is score increasing. So if we have like player, like the score of like 1, 2, 3, 4, 5, 6, so on, and then the ages are just some random number like 10, 3, whatever, like 4, 5, 3, 2, 9, 15. So if we know like this person's viable and we skip them, we know for sure that the next score is always viable, right? Like here, if we do it this way. So this might be actually the way. So if we take this person and we either take or whatever the score, we know for sure the scores are increasing, so the next one is always going to be viable. But if there's a case where the scores are tied, if we sort on age increasing or decreasing, does it matter as well? Let's say we sort on age increasing. So if we have like a bunch of ones here, and then we have like, so let's see, this one has a 10, or let's just do single digit numbers only to make it easier. So, and I'll just add some more numbers. So let's just say in terms of a tie, we do ages. Yeah, because players of different ages can have the same score. So I don't think it even matters. Let's say we even leave it like this. So how do we know who we can pick? And let's actually use the real example as well. I think that might be better. So let's take the scores and ages and sort. So basically we can have like these pairs. So 1, 2, or 1, 1. What's the other one? 3, 2, 5, 3, 10, 4, 15, 5. And we sort these in terms of score. So this is already sorted. So then we can say like, well, we can pick this guy for sure because the first variable is a score. Then the next score is bigger, so we know we can, yeah, so the problem here is, actually, we don't necessarily, yeah, so if we pick a score, like if we pick a score, we don't know what's the next available one, because if there's a score here, and we pick it, like we know we picked the 10, so the 10 is the biggest so far. But the age matters. Like, for example, if this is age 1 and this is age 2, like if this is a 1, this is fine. But imagine this was 10 and we earlier picked like 8 or something with a number of like 0 or whatever, and now we skip 10. Well, and then we have something like 11, 1, or whatever, like, yeah, 1 or whatever, like, or it says it was like this, 5, 2. So let's say we take this, or let's say we skip this, actually. We take this, then like we don't know what's the next one we're allowed to take, because like the next score might be like, or we do know, I guess we do know the next one we're allowed to take if we do take this, because we do have a number, so we have like, but no, I don't think we even do. So I think sorting on score just doesn't work. Yeah, because like if we skip things, we don't know like what's the second biggest score, like what's the biggest number something else took before this, things like that. So I don't think sorting on score works. So I think we have to do sorting on age. So score we're going to get rid of. If we sort on age, now do we want to do increasing or decreasing? Let's try increasing first, I guess. So this would be like 1, 1. I guess this is already, yes, this is like 3, 2, 10, 3, 10, 4, 15, 5. So this is sorted on age as well. I mean, in this case, it just happens to be the same way. This is increasing. So if we skip this, then like, what's the next one we can take? Or alternatively, what if we, so I think maybe instead of doing if we skip, what if we just say we have to, like, if you skip, there's complicated things that can happen. But what if we have to take? Like, what if we say every number we're on, we're going to take for sure? And we can have an algorithm like that. How would that change things? So if we say like 1 can take 1, and we're sorting on age. So how do we know, like, what's the biggest score we've taken so far? We really don't. Well, actually, no, so we kind of do. So if 1 can take 1, that means we haven't taken a score that is bigger than 1. Otherwise, this would not be allowed. Because like if we took a number that was less than 1, like let's say player 0 took 10, like this wouldn't be allowed because then we wouldn't be able to get here. So I think this is the answer actually. So basically, like if we take a number, then we know for sure a player with a smaller age never took a bigger number. Because our assumption is like we're only going to recurse to states that are allowed. But if there's a tie, then it could have happened, right? Like if there's like 110 here, then this could have happened. So now the question is, if there's a tie, which way do we want to go? And the answer is, like, if we take all of them, we want to have the biggest score we can at the end, because then we know, like, this is where we can go to next. So I think in case of a tie, we go increasing. So we sort on age increasing. In case of a tie, we have to stay increasing. Okay, and then from here, it's just simple DP, just take or not take. So essentially, everywhere we're at, we're going to choose to take, always. And then we're going to recurse to the rest of the numbers. And if they are a valid next move, then we'll recurse to those. And basically, the answer is going to be DP starting at every single one of these scores, like the max of that. So we're going to say DP starting at every one of these is going to be the answer. And we can do this in top down or bottom up. It doesn't really matter. I think bottom up is pretty simple because just like an array of scores. So let's do that. So let's first we need to get like this scores and ages combined into one. So I'm just gonna make a struct, call it like data, and we'll have a score that's an int, and we'll have an age that's an int. Okay, there we go. Then we're gonna take this and make an array of these. So and we can just say it's like, you can do this, initialize. So 4, 9, 0, and then we're gonna have a let s less than s, data, append a new struct. So data score will be scores I, age will be age is I. We also want to sort, so we're just going to write a sort function in here. I think you need this to be like static less than. static func less than. And then you basically define the comparator, and then you can call the sort. So this is like left-hand side data, right-hand side data. Returns a Boolean, I believe. So you basically need to return like, how does left need to be less than right? So if left-hand side age does not equal right-hand side age, return left-hand side age is less than right-hand side age. Otherwise, return left-hand side score is less than right-hand side score. Okay, so this will be sorted for us. So we can now do data sort. Okay. Then what we need to do is we need to have a DP. Yeah. So DP equals array 0 count. So basically we need, the base case will be like when we're out of bounds. So this will be s plus 1. Okay. We can fill this with 0, I think is okay, because we're never going to have less than 0. So this is fine. Okay. So now what we want to do is we want to say, yeah, we basically want to have a nested loop now. So, and we want to go backwards. So for I in stride s. So this is going to be like s minus 1, 0 by -1. We can basically say like what's the if we take this guy, like what's the most we can get. So that's going to be let's see, and then we also need a second loop. So for j in stride, so it's going to be like, or actually we don't need to do stride here, so this is like I plus 1, so it's like the next person we can go to less than s, or less than or equal to s actually. I plus 1 to s. Okay, so or actually we don't need to do s. We can do, yeah, so we can basically say we can do less than s. Okay, so we can say basically like here we need the actual score, so let cur equals like the score of the player, so dpi score, or actually not score, it's not dpi either, it's data I score. Okay, and this is what dpi is gonna equal. So dp, this is basically like take this and don't take anything else. Okay. And we are allowed to do that. This is basically just like take this and don't take anything else. Okay, so from here, if the age of the player is higher and the score is less than or equal to, we're allowed. I guess we can say when we're not allowed. So if the age is higher and the score is less than, we can skip. So if data j age is higher than data I age, and data j score is lower than data I score, then this is not allowed, and otherwise we're always allowed to go. So then the other case is dpi equals basically a max dpi, or take this guy and go to dp. So j is like the next person we're going to go to, which is j. And now we just return the max of all of these things. So we can just say var as equals 0 for item in data res equals max res item dot, or actually this is not data, this is DP. I think you can actually do return max DP, actually. Return max. I think this can take an array. Maybe not. Oh, why is this down here? Here? I think you can do this. We'll find out. Cannot find data. Oops. Error. I don't know what that's an array. Okay, so I think you just have to make this comparable. Argument number 2. Okay, so maybe, yeah, I don't know what this is, but okay, we'll just say this. I mean, we'll see how we can write it better later. Just get something working first. Okay. Yeah, so the trickiest thing here is figure out the sort function and also realize that you need to DP. It's not a take or not take. It's easier to just only recurse the things you take. And so there's these like different things you do, right? So call DP on every single starting point, and only go to things you take. Because if you take or not take, it wouldn't work. So I think this is the trickiest part. And to be fair, it's pretty difficult figuring out that like you have to sort on age and then you have to sort on score if there's a tie and like stuff like that. So yeah, this is basically n squared time and spaces n. Curious with the editorial. I'm guessing it has to be DP, right? So store the ages and the scores, sort the list, ascending order of the age, ascending order of the score. Yeah. Iterate through the players. You can add this player minimum. Okay, you have a previous. Interesting. Okay, so this is a 2D DP. Yeah, I didn't do it that way, I guess. Okay. Okay, so this is age pair 2n space. Interesting. Binary, not doing that. I honestly don't even know how that would work, but not going to go into that for this type of problem, maybe for like a super hard one. Okay. So the next thing is, as always, so you have something that works. Now, how do I clean it up? So this is where you can just give it to an LLM and see what you get. And here, there's not too much to clean up, but there might be some stuff. So let's take a look. So let's copy this and take a look. Okay, so this is small, not a huge thing. Okay, this is cool. So you can zip scores and ages just like in Python, and then you can map zip. So zip is like makes tuples, and then yeah, this is how you access tuples with an index because they don't have names. So it's kind of interesting. And then you can call it sorted. So this would have been cleaner for sure. Don't need that in this case. Best score. Then the rest of it's the same. So dp.max. I think I did max dp. Okay, interesting. So this is not needed. Oh, it's an optional. Okay, okay, interesting. And this would have worked. So this is like some small things in whatever language you pick to make your code cleaner. Now I know I can like map and use zip, and that would be better. And then that's how you do a max of an array instead of doing that other thing. All right, so that's going to be all for this one. So thanks for watching, and I'll see you in the next one.